welcome to lecture 25. We'll continue the lifting result today. So first, let us recall the setup. So we are given rectangles, which are like in the lifted domain. So they consist of like n pointers, and like we have like n bit strings, and each pointer picks out something in here, right? So we have rectangles, and we say that they are row-like if and only if like the rectangle under the image of the indexing gadget, which I'll denote by capital G, is just equal to all possible assignments that are consistent with row. So all possible extensions of row. So like just written out, so for all z's in 0, 1 to n that is consistent with row, we have some x, some pointers, right, and some y, so that the indexing gadget under x, y just evaluates. Right. And again, the picture you should have in your head somehow that we are on the right side, we have a lifted search problem, right? So we are looking at rectangles, our rectangle R, and we somehow want to go from this to the hypercube or a subcube of the hypercube. Okay, and so this is like just for a search problem mess. And this sub-hypercube that is somehow given if you're a row like row which is guaranteed the subcube, and which is what we're actually looking at. Okay.
And we should think of row as the falsifying assignment for a clause. Or
yeah, it's a conjunction.
Yeah,
it's a partial assignment. Yeah. And so then we have a random variable. We say that a random variable is h length if for all non-empty subsets on J. So I guess we have a random variable, right? X, which is in, let's say, M to the J, right? We have this random variable. Yeah. So we say it's h length is for all non-empty subset. If we look at the marginal distribution on this subset, we still have large min entropy. Just to be clear, like I reparameterized this for last time we talked about delta denseness, which meant that we had delta times I as the log n. I just reparameterized this h times k. Okay. So there's no confusion. And then we say that the rectangle R is row structured if you look at the marginal on the domain of row, then on the x side, then we're fixed. And furthermore, every z in the mapping of G, right? Like if we map R under the indexing gadget, we get assignments, partial assignments, or assignments in 0, 1 to the n, then these are consistent. Okay. And then on the free variables, if we look at the marginal distribution of the free variables, we are very dense, so we're 0.95 log m dense, right? This is near the maximum would be log m dense. We're 0.95 log n dense. And finally, we have that the y set is large, so its min entropy is some expression. Yeah, again, this is slightly different than last time. It's not very important. Let's do the next one. Computations work out nice. All right. And then we have the full range lemma, which is saying that if a rectangle x times y is row structured, so if it satisfies these properties here, then there is a unique x, right? A unique pointer thingy, right? So that x times y is row-like. So if we just look at one row of the rectangle, then we know that you can get all assignments consistent with it.
You didn't mean unique, right? You mean there is at least one. Like I can fix an x.
This exists.
Yeah.
Yes.
There could exist many, but at least one.
There's good. And then the other ingredient that we used last time was that we somehow, right, we start out with rectangles in our protocol pi, and we want to go to structured rectangles. And I somehow need to explain how this goes. And so, right, so we're given a rectangle R, this is our R. And then what do? We first we look at the x side, right? And what we do is we just find maximal subsets on n, right? So it's in the unlifted world, so to say, so that the min entropy on the marginal of x on this set I is small. So it's less than what we want, which is this 0.95 log m denseness, right? And it's maximal, and then we have alpha, which actually witnesses this. So this is just that the marginal distribution is equal to this alpha if the probability of this event happening is too large. And then we create our set x super I, which are just all the x's that are consistent with alpha I, and we remove it from x. Okay? So what this will look like is that we basically chop our rectangle that we had initially into like a vertical, I hope, segments. Okay. So this is our step one that we do here. So here we get just like x1, x2. And then in the second step, we each such horizontal segment, we split it further by somehow the assignment that we could get, and we fix the assignment on under the indexing gadget. So what I mean is that we look at all y's, so that g on the subset I on alpha plus y is a fixed thing, right? And this will give us our y. So what will happen is that we'll chop each block into further segments, and then we just output these rectangles. Okay. So something like this, right? Okay. This is the second step here. And then we get these rectangles, and then we have the rectangle lemma, which says that if we do such a composition, there exists some rows and column sets x error and y error, which have low density, so they don't contain too many rows or columns. So let me draw them. We have to add error set here, x error, that means y error. Draw them like this. And so that if a rectangle is not covered by them, so what I mean by covered is that like we need to completely be covered, right? So all these rectangles down here are covered. This one is also covered. This one will also be covered. These two are not because they're partially not covered by the Y, right? So that either these are structured, row structured, or some small row, or they're covered by the error set rows or columns. Yeah.
The density, do you want 2 to do something? Because density seemed before to be scaling like, or is the density like in the exponent now?
This, I want this 2 to the minus 2d log.
Okay.
This is the error. This is the error density, right?
Okay. So the error density will indeed be, okay.
And you should think of this as we're going to union bound over all these error sets. So this multiplied by the size of the proof should be something scale. Okay, so this is how White's chosen this way. So this is like estimate. And then finally we have this alignment property, so that if you look at any fixed row x, there exists as index at I sub x of not too large size, so that every rectangle that intersects the row x, we have the property that the main of row sub I is contained in this I sub x, assuming that R sub I is structured. Okay. And this one, so this furthermore property should be quite obvious, because if you pick any row here, then it's going to fall into one of these x categories, x sets, xi sets, right? And each one of them has small rows of rows per whatever. Okay, so far so good. This should have been a recap. So good. All right. Okay.
Can I ask just can we think about this as, I mean, in step 2, step 1, you're sort of picking out this, I mean, I guess we're not doing queries because we have some kind of Garg-like model, but the IIs that you find in step 1, those are in the communication sense coordinates that we might query. And then in step 2, you want to be able to, whatever we get back, you want to be able to support all bit strings gamma. And once I query and I get my bit string gamma back, then that's the sub rectangle that we're going to play in from now on.
I don't know if you say so. I mean,
It was a question.
Yeah, therefore I'm answering. I don't know. I answered that.
Maybe we'll see.
I think
Yes.
this is the right way to see it.
Yes. Seems to be more knowledgeable. That's okay. All right.
I mean, in some sense, you could view this. I guess we're not trying to do this, but from this proof, in particular, sort of one way of reading what you're trying to do, right? That if someone gives me a cutting planes proof of this lifted version, then I can actually use this to extract a prosecutor strategy for the original formula.
That's what we're going to do.
Yeah, and I think, and the point is like the IIs will be possible prosecutor queries, I think, and then the gammas are like things you can get back when you issue those queries.
Yeah,
what the defendant might tell
exactly. Yeah, absolutely. Yes, now I understand first. Yes, very good. Yes, I absolutely. Yes.
So now I actually got a question, answer back.
I also answered before. I said I don't know. It's not an answer. All right. So, okay. So, and we want to prove that for any search problem from 0, 1 to the n, where this is the input and we have some output, we have that the rectangle bag size of S composed with the indexing gadget is n to the width required to, like resolution is required to. Okay. Good. All right. So, what is our task? Our task is we're given a rectangle bag pi, right, of size n to the d, and we want to find a resolution proof or a conjunction bag of width. So, how do we do this? So first off, I'll just repeat again what we did last time, just so we're all on the same page. So, and first we're gonna ignore the error rows and columns. Okay. So how are we gonna do this, right? We have a proof pi, and we're gonna walk down the proof, and at every point, like every node here, is labeled by some rectangle R, and we're gonna maintain a rectangle R prime contained in R. R prime contained in R, such that R prime is row. And the size of rows. Okay. This is the idle time, and now we need to check that we're fine in the root. We need to check that we can do the step, and we need to check the accents. Okay. So first, the root. Well, I'm claiming that if you give the entire space to this procedure here that chops it up, it will just output the whole rectangle. Okay. So if the root, the rectangle is simply star to the n star. So we can just start there, and the prosecutor dependent strategy that we extract will start with 10%, which is S. Yes.
I know I'm slowing you down, sorry, but just to understand it, like we're gonna do a downward pass because we need to define all these beautiful structured rectangles.
No.
Or no, they already exist.
No, I didn't tell you anything yet.
Okay.
I just told you that we will maintain a row structure sign.
Yeah.
A row structured rectangle of each node.
Of each node. And
yeah.
This is what we're going to construct now.
Yeah.
And then once we've done that, we're going to look at the error set and sort of go back up and collect them. Is that no? Okay, good.
I want to ignore the error set. I'm not going to talk about it. Okay. I'll introduce.
But what we're doing now is we're doing in a top-down manner. You're building structured, beautiful R primes. Is that what's happening?
Yes.
Okay, great. Thanks.
I'm just going to maintain these R primes, which are row structured, and it's understood that on the other side, on the resolution side, our game state will just be a row. So in particular, we need to check that at the root, our game state is just empty assignment. And this should also be. And then the most interesting part is when we do a step, right? So how does it look like, right? We are at some node R, and we maintain a rectangle R prime, which is a row structure. So let me just draw R prime, right? So we have our rectangle R prime here. We know by the covering property of these DAGs that the two children will cover this rectangle, right? So we have like two children, right? Let's call them L0 and L1. And now in R prime, we know that R prime is row structured, which by the full range lemma, we now know that there exists a unique row so that X times Y is row-like. Okay, so let us fix this row. So let us look at this row. So we look at this row, which is called X star. And we know that this row is now row-like. And now I'm going to do the decomposition, or I'm going to apply this procedure to L0 and L1. Okay, so this is going to cut like this whole rectangles into rectangles, smaller rectangles, into row structured rectangles. And in particular, I can look at the rectangles that lie on the same row as X star. Yes. And so these are the rectangles where X star intersects. We know that in L0, the rectangles coming from L0, I guess there is also one. So the rectangles in L0, they have this property that because we fix this X, that all the domains are contained in this one subset I sub X. Okay. So what we'll do on the resolution side, we're going to query this set. Okay, we're going to query I sub X, let's call it 0, and union I sub X1. Okay. Query it on. And this will result in a new game state, which is called row sub. Okay. Now, because this row is row-like, we know that there exists a Y, so that X star, Y star under the indicator gadget will give you something consistent with row star. Okay. So we know that there exists a Y in, I guess, Y prime. It was R prime here. X prime, Y prime. We know there exists a Y, so that under the indicator gadget, G of X star Y is consistent with row side. Consistent with row star. Okay. This is just by the definition of row line. Very good. So let's look at where this is. Let's say it's here. Okay, so here we have Y. I guess Y here. Now I know that this point lies in some rectangle in L0. Now, so then we know that this point, the point X star Y, is in some rectangle L0I, right? which is row I0 structure. Okay. So now we can forget, and now in this final step, forget everything except whatever is in this, except the domain of row in the resolution. Okay, and we have again our invariant. With our invariant, it's that we are at a subrectangle of child that we moved to. In this case, it was L0, and the assignment is small by the rectangle level, and we only remember this. So this is really okay. So far, so good. All right. This should just be a review. This is more or less clear. And so then we have to also, so the last thing we need to check is really the leaf, which is kind of silly, and I ran out of workspace, which is unfortunate. And it's just a bit inherent here to have some space. So we have to check the leaf. So we need to check that whatever leaf is labeled with as an output is actually an answer to the unlifted formula, right? This side. And this is really just like retracing the definitions. So we are at a game state row with an R prime structured rectangle, a row structured rectangle, so row structure. And then we know that the leaf is labeled as an output, O in O. And so this implies that R prime is contained in the lifted problem, whatever output corresponds to, right? Now I can get a G to the other side. So this is saying that G, like R prime under the image of G, is contained in S of O. Right? That's inverse, I guess. But we know that G of R prime is actually equal to C inverse rho 1, because we know the R prime is row structure, therefore it is row-like, which means it is row-like. It has a row which is row-like somewhere here. The rectangle itself is also. Okay. And so this is showing that the row that we output is also a solution. That's the whole thing. That's without errors. Okay. Any questions? Right. Well, I need to tell you how we handle errors.
Sorry, I got the lift. Can you say the lifting again? Now that we're, because what do we want to argue?
So we want to argue that whatever we output in the lifted side is also a solution in the unlifted side.
Yeah, and where did the unlifted?
Well, we know that R prime is contained in the rectangle of the output O thingy in the lifted row. So in S composed with G inverse. Now we can get G to the other side, and we just look at the image of R prime under G and know that this is actually contained in S inverse of O. Okay, just by definition. And then we know that this side here, because we're row structure, which means in particular that we're row like, is equal to all assignments that are consistent with it. Okay. And this would correspond to the negation of the clause in case of the postulates. Also.
Okay. So we want to argue that, because at this point I'm not sure I know a lot about. I mean, we have an input Z, I guess. Or no, wait, what are we constructing? We're just constructing a resolution proof at this point. So I just want to argue that I've reached a
whatever we have should be completely contained within the solution. The subcube we have should really be contained in the subcube. I guess, yeah. All right. I believe you remember row like and each hens. So that's I'll remind you or ask me. Remember. Okay. Now we want to handle errors. Okay. So what we do is we will first now traverse this DAG bottom up topological order to create these structured rectangles. And we are going to remove, if we find some error set here, we're going to remove the error set from anything that is later there. Okay. So this will give us this property that whenever we move in the reverse direction, that the error sets shrink, which means that we maintain the cover property, which is really all we need at this step. That's basically everything, and then we just okay. So let me just quickly write it down. So how do we deal with errors? So we traverse our proof pi in topological order, from I guess they're called stink source to the root, whatever, what lingo to use. And that is called the rectangle is just R1 up to Rn to the V. Okay, it's the order we traverse them. And we're gonna create this error set X star error and Y star error. So every time we consider some Ri, what do we do? Well, we first update so we update Ri to just be Ri with these guys removed, whatever we have accumulated so far, they're empty. Ri minus, what is this? X star error times everything. So this is 0, 1 to the n union n the n times y error. Okay. So we first update our rectangle that we're currently looking at, and then we apply the partition scheme to Ri, and we actually output all the structured rectangles. Okay. And then we update X error to just include the errors we encounter now. So union X error. And similarly for Y error. Okay, is this clear? What happened? Now we can basically run the same argument. The only thing we need to check is that in the root we are still star structured, but here we're just going to use the fact that we are so dense on the so little density on the errors that even if you look at all of them removed, which will happen in the root, right? That we have removed much less than 1%. So we are certainly still very dense, and Y is very large. Okay. And the only thing that and yeah, and for this step, as I said before, if you go down, the error sets removed from the rectangles shrink, which means that you maintain the cover. Some of that. Okay, so now we have done the entire proof. And I don't think I was able to cover the error particle value last time, I guess. Any questions? So all we have outstanding is to prove the full range lemma and to prove the rectangle. Okay. Okay. I hope science means that you actually have it.
So now maybe it's not as clear that step one works, like at the roots
Yes.
that you're still.
Yes, very good. Very good. So for step one, you need to argue that your error sets at the roots that you removed are very few. Okay, so for this, you're going to use the density argument here, that you're going to say, well, I have like at most an n to the minus 2d fraction. So in particular, less than n to the minus 2d fraction of the rows that are in every step. But even overall, we have at most n to the d times n to the 2 minus 2d, many rows that we removed, right? Or fraction, whatever, which is still very, very, very small. So certainly we are still very dense and very large. That's all we need. You buy this, right? Mm-hmm. Anything else? All right, we can start with the rectangle lemma. And what would you do if you wanted to prove the rectangle lemma? This is serious, I'm asking. I expect an answer. Similar to how Jakob expected now. How do you prove it? I mean, what is the main task? The main task is to find these error sets so that, right, everything is good. What would you do? Most naive answer wins. Trust me.
Find a place where there's an error and try just removing that and see if it works.
Yeah, exactly. So what you do is on the X side, you're just going to say, well, if I have anything where row I is too large, I'm just going to throw it into X error set. I do this a bunch of times until I'm done. Then I look at the Y set, and there on the Y set, I'm going to say, well, what could go wrong there? I need to make sure that we're not too small, right? And if any of these Y sets is too small, just put it into errors. And it just works. So, all right. So we're looking at the proof of the rectangle then. So first, I have to define X error. So while we have still a rectangle Ri, so that Ri equals X times Y, such that the set I, super I or sub I is small, is large, sorry, is larger than 40 times D, then just add X to X error. Okay, this is the most naive thing you can do. Okay, this is defining X error, and then Y error similarly. And as long as there exists some Ri again, Ri equals X times Y. So as long as there exists the rectangle, such that the size of Y size Y is less than what we want there, will be 2 to the n times n minus the size of I sub I minus 5d log n. Then add it, okay? Add Y.
We first run 1 and 2 like on the right thing.
Yeah.
You run the algorithm, and now you just go over, let's see what happens, and you classify the bad steps and collect them.
Yeah. Okay. Very good. So what do we need to prove? We need to argue that any remaining rectangle is actually a row I structure for some row I. I claim this is kind of obvious. So what do we need to show? We need to show that that it is fixed on the domain of row, right? But this is just how we chose our X and Y, right? In particular, the Y we chose so that we are really fixed on the row. So that seems fine. The second part, on the free part, we need to argue that we are very dense. Climbing, if you're not dense, then you did something wrong here, because then you did not choose your set capital I maximal, right? If you still have a subset on which you're not dense, then you could have used, like, added this to the I set that you define the rectangle with, and you would violate the maximality. So this density should also be clear. And finally, Y large, well, you know, otherwise it's in the Y error. Okay. So all that is left is to argue that the domain of row I is small, but this is how we chose our X errors. So this should establish somehow that the rectangles left over, they're very nice. Okay. All right, so all we need to argue is that we have low error set density. Okay. So it remains remains to argue that we have low error set then. All right, so let's start with the x side. So what do we want to show? We want to show that x error, the size is bounded by m to the n times 2 to the minus 2b. Okay. Okay, so either x error is empty, in which case we're done, and otherwise we know that there exists a minimum j, so that we added xj to the error set, to x error. Okay. So this implies in particular that this set here is large, right? So I sub j is large. All right. So I'm claiming that x super j is at most x larger than j. So this is just the union of all xj greater or equals to j, or xi greater or equal to j, right? And times 2 to the minus 0.95 size of ij log. You see this? So as a hint, this thing here shows up here. So right, xj is equal to the set size of x larger than j times the probability that you are actually in this set, right? And that's the numbers. And okay. All right, that's the first one. So in particular, we know that the mean entropy of xj is larger than the mean entropy of x greater or equals j minus this one. Y minus j. Okay. At the same time, we also know that we have an upper bound on this quantity here. Namely, we know that n minus size of ij times log n is clearly an upper bound on this, right? That's just the maximum entropy of this thing because we're fixed on this I sub j. And now just rearranging gives you the desired error quantity because you know that x error is bounded by x greater or equals to j. Okay, so we know that the size of the error set is clearly bounded by the size of x larger than j because we chose j minimal. But here we reuse that we chose j minimal, so we know that the whole error set has to be contained in this set. And now you rearrange this and you get the desired. Okay. You get the signals. And minus.
Sorry, what was this x greater than equal to j?
So x greater than equals j is just the union of.
Is that what we came before?
Yeah, no, after.
Oh,
After equals I greater equals to j.
And then you're picking j minimal such that what? Is that the last time that's the last error?
It's the smallest j, so that xj was added to x error.
But the first time we got the first time we picked up an error set.
Yes.
Okay, because there somehow these j's are like there's a for loop over on the
Yes.
right, and these are j's, the index. So the first time we added an error set, you look at how. Okay.
Right. And so we know that I sub j is large, which we'll use somewhere here, going from this to this, whatever. And we know that the size of xj it's upper bounded by x greater or equals j times the probability that we're actually in xj, right? And so then you actually get the corresponding quantity on the mean entropy side. And we also have an upper bound on this because we know that we're bounded, we're fixed on this isotope. Okay. And then you rearrange, and we observe that x error is contained in x greater or equal to j because we chose j minimal. Okay.
I still struggle a bit to see what will end up in the error set, but I don't know if that is important. I think we had this very stupid, in the communication protocol, we had this very stupid case where Alice could send the number 42, which meant actually my index set is exactly this. And then we would avoid that because if Alice, by sending the magic number 42, told Bob exactly what her integer was in all coordinates, then things just collapse completely. And I wonder if that is one of the rows that wouldn't end up in the error set in this setting. I think so, but I'm not sure. Because then in particular, yeah, I don't know if it's helpful.
Yeah.
I'm struggling a little bit with the error set.
I don't understand. I don't understand enough about the normal answer. See. Okay. Right. So then it remains is to show that the y error is small. Yeah. Sign y error. So we know that so we're going to do an encoding argument, okay? So we know that every yi gamma is uniquely defined by the triplet I sub I, alpha I, and gamma. Okay. Now let's fix a size k in RTD. And let's just count how many of these we have. Okay. So how many I sub i's do we have of size k? So we fix k, and we understand that the size of I sub I is k. So how many I sub i's do we have? Well, there are n to choose from, and we choose k, right? It's just a subset. The alpha I is just an assignment to k variables. So this gives us a 2 to the k factor. No, sorry, there's an n to the k factor, right? Because alphas are indices. Right? Alpha is an assignment to the x variables, so it's the indices. But then gamma is just a Boolean assignment. Okay. So clearly, what you can do is, so by a union bound, we can upper bound the number of things in y error by something like, well, sum from k equals to 1 to 4td. We have this many such y super I gamma, and each time we add at most this many columns. So we have to multiply this by 2 to the m minus k minus 5 n. Okay. Now you do your computation and you see that this is. You want me to do it? I wrote it down, so I don't have to do it because I'm sorry, but let's see. So right, so we have something like minus 5d log m here. And here we get at most, so what do we get here? Here we get a 2 to the 40. No, so this is so right. So we can write this certainly as 40d times the maximum term. This should be when k is small, because otherwise we have an exponential in n factor here, which wins. Right. So the smallest is if we get a 2 to the m times n minus 1 minus 5, like 5d log n. And then what do we pick up here? Well, here is an n factor, here is an n factor, here is a 2 factor. Right? So certainly this is upper bounded by, say, 2 to the 3 log n, something like this. Mertz.
So, fine. We'll get it later.
Okay. Should give you.
This is a little bit counterintuitive, but you're saying suppose everything on the y side is bad, pretty much.
Yeah, but every time you add in such a small set, it's somehow just a small. So then you just count everything correctly. I'm sure I mess up. And then but then erase this fine. So but like the point is that yeah, you can just count the y error sets by how many y's do we have. Each time we add so little, it just doesn't. This proves the rectangle. And I think it's time for a break. Go back from the break. It was pointed out that there's a slight mistake here, or was a slight mistake here. So we used before we used like this probability and upper bounded by the side. And this is clearly not true because we only have a lower bound, but we can just use the fact that a conditional mean entropy is lower bounded by the mean entropy minus the log 1 over the probability of the event actually. And yeah, the justification is just expand the definition. So if you look at log 1 over probability of x, you can write this probability of x conditional e times probability of e, and then you can separate this into logs and rearrange things, and then you take a min or a max in the mean entropy and you see that this is fine. That was maybe a bit quick, maybe way too quick. But yeah, you can just check this offline, but then you actually completely get this fine. Good. All right. So now we actually come to the fun stuff. I think this was fairly boring. Or, I mean, yeah, it's like you just create the obvious error sets and then you analyze it in a straightforward way. Nothing's really happening. Yeah, but I think like proving the full range lemma is actually fun. And I'm not going to use the original proof by GKKS or GG, I think GTKS, but I'm going to use the lifting with sunflower proof. But I'm not going to tell you anything about sunflower. So I'm hiding that there are sunflower. But yeah. It's nice and great for the ever. All right, so we're done with this. So I guess I have a bit more space, but I'll also erase this stuff here. So all right. All right. So we're given a rectangle R which is a row structure that we want to argue that there is a line so that it can get like all assignments that are consistent with what it is. Okay. So okay, let me just write this once more so it's clear. So we want to argue that there exists an x in x star in x, so that an indicator of the x star y indicator x y x star y is equal to C inverse rho of 1. So all assignments that are consistent. Very good. So we want to prove this by contradiction. Okay, so by contradiction. What does this mean? So we're saying that for every x in x, there exists some assignment on this side, right? So that there is no y that actually results in this assignment. Okay. So let me just write this down. So what we're saying is that for every x in x, there exists some assignment z in 0, 1, 3, n. So this z is on the right-hand side, right? Unlifted side. So that for all y in y, we have that. Let me write it like this. And it's different from what I'm saying that so for all y, if I look at the indices given by x, right? So this is just the output of our indexing gadget is different from z. Okay, so a picture to keep in mind. So how we want to think of this is that we want to think of y as given in a matrix, and this matrix will have dimensions n by n, and it's a Boolean matrix or whatever. There's a Boolean entries. Okay, and so now what does an x do? An x just identifies one cell per column, right? So it says like, oh, this is the cell that I care about. Maybe it says this one, this one, this one, this one. Okay, so x identifies these cells. And all we're now saying is that, well, for all y's, if you look at these cells, you'll never find a z. Okay? And no, for all y's, you say, yeah, I think that's it. Okay. So we never find the z value in these boxes. All right. But you can think of this as a constraint, right? I can tell you like, okay, find all the y's so that this property is satisfied. I can think of this as each x gives me a constraint, and now I want to say, well, how many y's are there? And this is what we'll do. We'll just say, okay, fine. We have these nice constraints for x, right? These constraints y, and now I want to say, well, then y has to be small. Okay, which will contradict our assumption that it's actually. So,
are you going to prove that most x's are fine?
No. I mean, I assume that for every x, this is the case. The conclusion can only be that, well, yeah, okay, fine. I guess you can do, yes, I mean, it depends on the parameter. If you play, yes, right. Or at least
Maybe.
There are several of them. They should be true. Yeah. All right. Okay, so what do we want to say? We want to say because the constraints x have large lockwise mean entropy, whatever, what do we call it? Denseness, have large H denseness, density, whatever. So because these x are well distributed, let's read that almost like uniform, and it implies that there are few y's and satisfying these constraints. Okay. All right. There's one slide. Yeah, so okay, so fine. So we are given these constraints, and now I kind of want to understand, well, what is the worst choice of z's for us? Okay. And I'm claiming if the z's are all the, say, the one string, if z is equal to all one, this is the worst case that can happen to us. Okay. Let's do a very silly example in a sense that suppose we actually just had a single bit. If I claim once that, oh, this is different from 1, and I say once that, oh, this is different from 0, then clearly if I only have one of them, I have a larger set y. Like, right, more possible assignments to this one thing. Okay. Instead of having two different ones. And you can generalize this, and like, I think if you want to think of it combinatorially, the easiest way to see this is that if these are all equal to 1, then the constraints somehow tell you that some subcube is ruled out. And if they're all equal to 1, then the subcubes intersect maximally. Okay? Which means that you rule out the fewest y's. Okay? So yeah, they all point kind of into the same direction of your cube, and so therefore you're fine. You can prove this formally by saying that, well, if you have a CNF, right, you can think of this as a CNF, say, and then you flip all the variables to positive or negative, right? And then you can see that your assignments, the number of assignments will only increase by induction over flipping. Right. And it's very fun. I'll not do it. So yeah. It'll take you 5 minutes. All right. So really what you want to analyze is the event where all these z's are equal to 1. Yes.
Are you saying that this is the worst case, or are you saying without loss of generality, let's fix this vector?
This is the worst case for us.
Okay. It's right, important to understand that this is,
okay.
Because I don't get it.
No, it's like you have your cube, and
I mean, it seems like the problem seems completely symmetric with respect to whatever the bits might be.
There's nothing special about the one string specifically. It's just that it's constant across all. Across all of them. That's excess.
Yeah. I think you just want every bit to be in the same direction.
Yeah.
And that's enough. Yes. So the point is just that every time you rule something out, you rule out some subcube, right? Like down here, you're ruling out this cube here.
Mm-hmm.
And now what I'm saying is that if they all point in the same direction, you're going to have these constraints maximally intersecting, right? Because they're going to align to the same piece of the cube. I mean, I cannot really draw this, but yeah, because yeah. If you want to do this formally, take any CNF with flips of variables.
I think I'm sorry. Okay, I still need to think about it, but I'm starting to see what you're saying.
The other way of seeing it is take any CNF with variables with negations and positive things, and then you flip them all to the same sign. Then you should be clear that you somehow the assignments that you rule out or are satisfying. It's very confusing now. It's going to increase or decrease. So just in the correct direction. I like to think of it like this, that you want to have maximum intercept. Yeah, formally can be proven by CNFs setting all the bits. Okay. All right. So you want to analyze and the event when we choose y uniformly at random from 0, 1 to the n, 0, 1 to the m times n, right? This is the domain where we use our y from. And we want to say, well, each x, you can think of it now as a set that contains these red boxes, and we want to analyze what is the probability of all these x's not being contained in this random one. Okay. We want to look at the probability that over the choice of such a y, that for all x in our family x, we have the property that x is not contained in y. Not to find this special. Is the statement clear? So I'm going from x being somehow an index in m to the n to a set as indicated. So and then I just want to analyze what is the probability that x is not contained, because ones are now indicating that. And for this exactly this statement, you can analyze by something called Janssen's inequality. Jansson. But I don't know how to call it. Janssen. You know, the guy from Uppsala. If I remember correctly. So we can actually analyze this to be exponentially small in minus mu over capital lambda thingy, where mu is now just the expectation of the number of contained set. What is this? We know that this is equal to the size of x, just by linearity of expectation, I guess, times 2 to the minus n, because each set will have n entries, and with probability 1/2, we're going to include each of them. And lambda is somehow analyzing how two events correlate. Yeah, some notion of correlation. So we have a sum over all events ij, so that xi intersected xj non-empty. Okay, so we're looking at sets where these red guys intersect, and then I'm just going to look at what is the expectation that both these sets are actually included. What is the expectation of the indicator xi union xj actually being contained? Okay. Right. So all we need to do is we need to bound lambda. Then we're done. All right. And so here we're actually going to use the fact that our constraints are very dense. Okay, they're very well distributed. And just to mention this, like if you know spreadness notion, like how well the sets are spread, and then mean entropy and this denseness definition and this spreadness is the same. It's just a different thing, slightly different. So all we're going to say is now that, well, if you look at the intersection of two sets, then there cannot be too many sets that evaluate to the same thing on this intersection, because if there were too many, then your probability would be too high and you wouldn't be so close. Okay. Okay, so let me say this more formally. So let us consider a set of A points. Okay. Now what I want to frame is the number of sets from X intersecting in A in this set, let's say capital A of points. So the number of sets that can intersect in this one set is bounded by something like the size of X times m to the minus 0.95 times the size of X. Okay. And this is just probability But like if you sample a random set and you look at, oh, what does it look like on these sets? Like you would just have too much probability there mass otherwise, and you would not have such low min. Like if you look at the marginal one. Right? Like I mean, what are we looking at? We're looking at a marginal here on this subset. Yeah, what is the probability of that? I don't know. I'm not
So file one is just a generalization of this.
Yeah.
To larger.
Yeah, this is careful. Yeah, so what we're analyzing here is basically the probability of finding an empty sum problem. So this calculation will not give us the correct bound. You want to do sunflowers also for this. Otherwise, you can go to the sunflower and not give slightly better bounds or a version or some version. Okay. So anyway, so our mean entropy assumption somehow tells us that our sets cannot intersect the same things too often. And now we can just count somehow this lambda set and we'll get it with exponential. Yeah. So let me just do this real quick. So how can we bound our lambda? I can write lambda as size of x. So I take one set and then I choose the size of intersection from a equals 1 up to n. And we have a choices, like n choose a choices, right? Then I have this is the how many of these sets actually intersect in these points. So this is another the size of x times n to the minus 0.95 is a. And then what is actually the probability that all of this is included in y is just 2 to the minus 2n, okay, because this is how large the union of these sets is. Okay. And now, I mean, yeah, now you'll see that this is actually something like mu squared, then x here, the 2 to the minus 2n. So we can collect these terms, right? Mu squared factor, and then we can use the binomial theorem to say something like this is bounded by 1 plus 2 divided by m 0.95. We get n minus 1 because we start at 1 and not at 0. Right? And we can bound this by something like mu squared. You do this thing twice, the exponential and down again. And we get something like mu squared times 4n divided by m to the 0.9. Okay. Now, if I did not mess up, it should give us a nice one. Should have written squared unit. So now we get, so what is our
There's no, you don't have an exponential thing there somewhere.
No. I go once exponential and then down again. Right, I can write this as exponentially in 2n divided by m to 0.95, and then I can go down again. So I can write it as 1 plus 2n over m to 0.95 minus 1, and then I'm just left with this factor. And you have to add some 2 there.
You just develop it.
Yeah, okay, fine. You can also do that. Yeah, you can write it as
terms.
Yes, sure.
You have 1 minus 1.
Yeah.
There's some kind of Taylor expansion thing.
Yes.
Yeah, you take the first term.
Okay, but the point is that we now get that this is bounded by something exponential minus 4n over m to the 0.95. And then, hey, no, right, m to the 0.95 divided by 4n. Okay, so now if I choose n large enough, right, so take roughly quadratic or so, then I will get contradiction with the size of y. Because what is the size of y? Well, we know that the size of y is going to be at most 2 to the m times size of rho inverse star well, yeah, whatever. We do some calculations. That's fine. Yeah. Sorry. And yeah, no, it's like yeah. Yeah. Okay. I mean, yeah. So the size of y is on the and then minus 8 and no. Okay.
100 from below.
And no, no. I mean,
And the point you're saying that y having this property, it cannot be larger than this, and then we
Yeah.
expect to run into a contradiction because y is larger than this.
more.
That was from this and not from that.
No,
Yeah.
Sorry,
Yeah.
From this is an upper bound,
Yeah.
and then you have a lower bound here, and then you find.
Yeah.
And so one last thing I wanted to say is that this bound can be slightly improved. Or I mean, no, actually this bound can be slightly improved. And if you use now the stuff from the sunflower business, then you'll get slightly better parameters, and you can actually push n to be n to the 1 plus epsilon. You can choose n to be roughly n to the 1 plus epsilon. And if you use the sunflower stuff, but not with this main application again. So here we're stuck at, I think, roughly n stuff. That's all. Do you buy this proof? I think it's very pretty. Like I'm like amazed how clean this is.
So what did you do again? You're just collecting. It still seems okay. So first, I don't. It seems to me that you're just. Okay, I don't know if it's fruitful to discuss this. It still seems to me that you're just fixing a Z without loss of generality. Let it be the one once.
Like also stepping Y.
Yeah.
So I really think that's what we mean, because otherwise, if you have another Z, you're just going to flip things in your head. Like it's not the worst case; it's just a good vector to think about.
They can, yeah. Like I mean, this Z depends on X, right? And I want to say that we can consider always the same one, no matter which one, just fx1. Right? Like, I mean, Z depends on X here. If I want to say, ignore that, it does not depend on X, we can think of it as just all ones or any fixed string.
Yeah, because we need the whole range, so we can choose whatever we want. Is that what you're saying?
No. To argue this, you need to somehow argue that this is really the worst case they can have. And this is like, you can look at what Y's you rule out, and if they're always the same, then you have the maximum intersection of these two. What do you rule out? Think of it as a CNF, right? This is immediate. You can think of this as a CNF. I guess it's a negation. So then you're interested in what is the maximum number of satisfying assignment. And if I flip all the literals one by one to the positive one, right? Like if for every variable, I just say, okay, I remove all the negative literals and replace them with positive ones, then I'm claiming that the number of satisfying assignments increases. I see. That's how you formulate.
Yeah. I think that makes sense.
This is just so that it's easier to see that it wouldn't change. If it was any constant.
Yeah, you can
Yeah.
you can choose any constant
Because you can see just all one, it's satisfying one, but you can just flip the.
Yeah, you can say,
literals.
okay, the Z ones, I want the positive
Yes.
ones on X, I want the negative
Yeah.
ones on Y, whatever. Yeah, you can pick any fixed one. Yes. That's
Okay, good.
yeah. I don't know. I like to think of it as you have constraints. You want to know what is the worst case. For us, the case that is also the same. And then once you have that, it's really so simple. I mean, I really like it. It's really.
Okay, but what did we see? So you.
That's ended.
I think I think I understood one thing. The thing I was worried about before also about reaching the leaves. So let me see. Let me try to rephrase that and see if you agree. Because when we're reaching this lifted dag, you're reaching some point, and you have some. The point is this: you have some rectangle in mind, right? But over on the unlifted side, you're just building your rows, which correspond to clauses, and we have no idea what a priori they don't correspond to anything. Right, and now you hit the leaf, and you have a row in your leaf also, which is a clause. And you want to argue that that clause is actually now, in order for that's sort of what you want to think about as your answer. When you reach a leaf, your construction have given us a row, which means that it has given us a clause. A priori, we have no idea whether that is a clause in the CNF formula we started with. You need to argue that this row actually identifies a clause in the original formula. Otherwise, we're screwed. In particular, I want to say that whatever this lifted protocol answers is actually a subclause of this row clause that you built, right? We need to argue that. Are we?
Yeah, we argued this
on the same page?
Yep, you're on.
Yeah.
Yes.
Okay. And the reason, okay, so why do I know that the protocol or whatever I view it as, how do I know that it's answering with a subclause of your row? Well, because of the full range lemma, it couldn't answer with anything else, because for anything else due to the full range lemma, like there are lots and lots of weird inputs that project to other things. So like the only safe thing to answer is actually a subclause of your row. So like so we know now that your row clause is actually a super clause of some clause in the formula, namely the clause that the lifted protocol answered with, I guess. So maybe this is what you said, but I didn't understand this before. Could you say something again about Jansson and why you were interested in this lemma? This was in the statement of this is some kind of variance measure, xi, xj, the union thingy. I didn't get that part.
Well, I mean, there's just Jansson's inequality.
Yes, which I don't have in cache.
Yeah, it's exactly this what I'm saying here. So the probability that you have a set system, and you want to look at the probability. What is an upper bound of the probability that nothing is contained in your sample thing? Is exactly the statement of Jansson, and you get the definite exponential minus mu squared over lambda,
Where lambda is
this like kind of
expectation.
yeah, it's like some kind of correlation measure of how correlated are these sets.
Okay. And then what was the calculation that
So
we
the
did? We
calculation-
calculated lambda?
Yeah. So here, right, we have lambda, and I'm saying that there's probably an inequality, but we're just counting how many sets we have, and we crucially use the fact that we are at log n dense, which means that we're like we cannot answer too often the same thing, because if we would do this, we would have we're too likely. Yeah, the probability that on that marginal you would actually output this set A is too likely. Okay? So you know that you have an upper bound on how many sets actually intersect in a given set. Yeah.
And then we did the calculation, we got this expression, we rewrote it to an exponential, we did a Taylor expansion, and then boom.
Yeah, and then you get what we want. See that.
Thank you.
Like, yeah. So yeah. And then the amazing thing is that this Fullerene lemma, like the previous proofs, are you need to work, and here we're not doing anything. We're just viewing it the correct way, and then you suddenly apply the answer. I think it is really
Okay. And we didn't do triangles, but you're saying it's mostly, if we understand this, then triangles will not.
I mean, the full range lemma is the same. So all the changes when we go to triangles is that the rectangle partition scheme becomes a bit more complicated. And instead, what you're going to do is you're going to decompose your triangle into covering with rectangles, so that you somehow. So what are you going to do? This is a very rough description, but so you're going to get a covering of rectangles. And not really sure how to draw this correctly. And you somehow have the property that if you look at the triangle within this rectangle, then there is still a large rectangle within this triangle. Okay, and then you basically you pass. Yeah, you can play this game now. These two rectangles and basically the same. Yeah, you have to be a bit careful and make sure that this kind of works going from other between the rectangles.
Is that a little bit like the argument of Sokolov in the cutting planes law bound for?
I don't see that.
Okay, sorry. Then it has nothing. Maybe it has nothing
If
to
you
do
can
with.
explain to me, I'd be interested.
I don't know. I do remember like you have those slabs, and then you have rectangles that go over them, and you consider also sub triangles. I remember it that way, but maybe it has nothing to do with it.
So there,
Yeah, I'm sorry.
Right. Don't be sorry. It's fine. So right, you look at one row X, and then you look at what is the minimum number of axioms that somehow cover this stretch here.
Yeah, exactly. But then when you know, because then you have this tree, right, where you recurse over sub-rectangles, sub-triangles.
But there you're always working with axioms.
Okay. Yeah, you're right. Yeah.
And here you just have like structured rectangles.
Okay.
Right. So it's not obvious to me how to read it. I don't know.
One other thing that I don't see, but maybe it's we need to just understand this better. Again, if there's like a protocol version of this, and this works for real communication, and we can also not just do it for lifting, we can do it for lots of other gadgets like inner product, and I guess there have been results saying that for any gadget that satisfies such and such properties. And somewhere hiding inside what we've seen today and last time is the fact that this works in a DAG-like setting. And because of this, this would not extend to, for instance, inner product or other gadgets. And I guess it already came up, but is it possible to say anything about like what breaks, what makes this, so like what are the challenges of the DAG-like setting that makes us want to use index and nothing else?
Let me repeat again what said often. I don't know much about lifting. This was an excuse for me to learn this stuff. So I cannot answer. I do not. Good.
Thank you so much.
Yeah.